Okay, in this video we're going to do section 5.3, and they're going to go through some new techniques for integration. So it's really for the more difficult problems. So the first thing we're going to do is talk about the general power rule for indefinite integration, and the alternative method we're going to use is called the U method, or U substitution. So here's our first problem. So what you want to do is you want to look at the more complicated of the two component parts. And so the x squared minus 3 under the radical is the more complicated. So what I'm going to do is I'm going to say, okay, I'm going to define that as my u. So u is x squared minus 3. Notice I don't have the radical. So du dx, that derivative, is going to be 2x. Okay, so we want to get dx, this bottom part, by itself. So you can kind of think of it as this. What I know is that du equals 2x dx. So to get dx by itself, divide by 2x. So whenever I have a dx, I can substitute in a du over 2x. Okay, this will all make sense in a second. So what we're going to do is we're going to rewrite this problem. So the 2x stays where it is, but now x squared minus 3 I'm going to write in a shorthand manner, and I'm going to put in a u, and the power is the 1/2. Then I have dx, and we just went through how dx is just du over 2x. So nice things are going to start to happen. Notice that this 2x and this 2x can cancel. So now what do we have for our problem? We are just going to take the derivative of the integration, and it's indefinite because there are no endpoints, of u to the 1/2 du. Okay, and I'm going to make that look a little clearer because that does not look like a 1/2 to me. Okay, so this is 1/2. Okay, so my antiderivative will be, so just use your power rule, u, 1/2 plus 1 is 3/2, divided by 3/2, or times 2/3, and then don't forget the constant of integration. Now we can't leave it like this because I really need to get back to the original problem. So at the end of the problem, I'm going to switch back to x. So I'm going to erase, well, what I'm going to do is I'm going to cut this out. So I'm going to take this for right this second and just say, let's cut that. Okay, so now let's put in our x again. So what, well, I should up here define it. So remember we said u was x squared minus 3. So we're going to replace our u with x squared minus 3. So now our antiderivative, the answer, is going to be 2/3, and then you're going to have x squared minus 3 plus the constant of integration. Okay, so that would be your capital F of x. Okay, so not too terribly bad. Let's go on and do another example on the next page. So this is going to be another U substitution. And so the most complicated term is the x squared plus 5 to the 3rd. So why don't we define u as x squared plus 5? So then du dx equals 2x. So what does dx equal? Well, du equals 2x dx. Divide by 2x. Divide by 2x, make this bigger again, and you can see that dx will equal du over 2x. So I'm going to need this, and I will need that. Okay, so let's rewrite our problem. So the 4x stays. If I wanted to, I can pull out the 4, I guess, but I'm just going to leave it be for right now. And the u is going to be raised to the 3rd power, and then my dx is 2u over is du over 2x. 2x goes into 4x 2 times. Now at this point, this is the better time to pull out the 2. So I have 2 u cubed du, which is a much easier problem to take the antiderivative of. So just using the power rule, I have 2 u to the 4 over 4 plus c. Okay, so the 2 and the 4 can reduce to a 1 and a 2. And we have to replace the u with the x squared plus 5. So our final answer is going to be x squared plus 5. All of that is raised to the 4th power plus the constant of integration, and I'm dividing it also by 2. So that takes care of that second problem. Okay, here's another problem. So by this point, you may want to pause the video, see if you can figure it out yourself, and then restart the video and see if your answer lines up with mine. Okay, so I'm going to pick out the most complicated section, and I'm going to make my u equal to x squared plus 7, so I can do my u substitution. So du dx equals 2x, yet again. And I have 2x dx equals du, so dx will equal du over 2x. Okay, so now we're going to do our replacements. Don't touch the 2x. For your x squared plus 7, that's going to be u, and that's raised to the 4th, and you're going to replace the dx with du over 2x. And look what happened again, which is very nice. So now my integration is just u to the 4 du, so my answer is going to be u to the 5 over 5 plus c, but don't forget you're not finalized until you replace your u, and that's over 5, and you need your constant of integration because we did indefinite integration. So there are some 3 nice little problems for you to go back and think about. Okay, so now we're going to up the ante a little bit, and we're going to try this general parallel rule in the situation where we have definite integration. So that means that we have endpoints. We have a's and b's, and you can see we have an a of -1 and a b of 1. So I said at the end of the problem, do not switch back to x. And the second big point, you have to recreate your 1 and -1, and we'll talk about that in a second. So I think the most complicated thing I have is this denominator, which is going to be x squared plus 2x plus 2. Okay, so then my du dx is going to be 2x plus 2. So doing the math, I know that du over 2x plus 2 will equal dx. Okay, I'm just going to get rid of this one down here. Alright, so let's start changing things up. So first off, we're going to write our integration symbol. The x plus 1 does not change. It is still x plus 1. The denominator changes to e to the cubed, and the dx is now du over 2x plus 2, but looking at my numerator, I'm going to write it as 2x plus 1, and you probably see why. Okay, notice I did not put in my endpoints, and this is because those endpoints only work with x's. We're now doing u, and we're not going to switch back, so I have to have it in terms of u. So, if my x is -1, then I'm going to plug it in to this expression for u and get what the u endpoint would be. So I'm looking for the lower one. It's not -1. What is it? Well, -1 times -1 is 1. So 1 minus 2 plus 2. It looks to me that that is a 1. So replace that. Let me just get to where we are. Here we go. Okay, replace your -1 with a 1. Now we're going to do the same thing for 1. So 1 squared is 1. 1 plus 2 more is 5. So notice I have different endpoints. Okay, so now let's cancel this with this. And what I'm going to do is I'm going to bring up my u cubed. So my expression is, and let's bring out the 1/2. 1/2 can come out. This is u to the negative 3 du. Okay, so, and I'm going to integrate it from 1 to 5. So that's going to equal, the 1/2 comes back now. I have u, if you add a 1, a positive 1 to negative 3, I get a negative 2. And then I divide by negative 2. And I'm going to evaluate all of this from 5 to 1. But first I'm going to clean it up a little bit. So what I am seeing is that I have negative 1/4. I'm going to put my u squared in the denominator. Okay, and then I'm evaluating it from 5 to 1. So if you plug in, you should be getting 25, negative 1/100 minus another expression that's going to be negative, so it's going to be plus 1/4. And if you do all the math and get to like terms, you should be getting 6/25 for your answer. Just check, make sure that you can get that. And let's go on, we'll do problem number 5. Okay, so we're going to do a u substitution, and we're also going to switch out our endpoints and make them equivalent values of u. So the most complicated section is the denominator. So u will be equal to x squared plus x plus 1, and that means du dx equals 2x plus 1. So du divided by 2x plus 1 will equal dx. Okay, so now let's start substituting. And I'm not going to write my endpoints because I had to change them up also. And actually, we can do that right away if you want. So negative 1 squared is 1 plus a negative 1 is 0 plus another 1. So this bottom number becomes a 1 also. Okay, let's do a positive 1. So 1 plus 1 is 2 plus 1 more is 3. So our new endpoints are 1 and 3. Okay, so now we're going to write. So x is still x plus a half. Okay, and then my denominator ends up being u to the third, and my dx is du, and I see it's 2x plus 1. Why don't I pull out the 2 and make that x plus 1/2, and you know why I did that, right? Because I want to cancel those. So now I can cancel these guys. I can rewrite my problem. So I still have endpoints of 1 and 3. I now have a half I can pull out from the denominator right here. And I have u to the negative 3 du. Okay, so take that integration, and you should be getting, let's bring the 1/2 back in. This is u to the negative 2 over negative 2. And I'm evaluating that from 1 to 3. I'm going to rewrite this as negative 1/4 u squared. And when I plug my numbers in, you should end up getting negative 1 over 18 plus 1/2. And when you do that math, you should be getting 4/9 for your answer. Okay, so that's a second example of u substitution. And remember, u substitution for direct integration requires you to also switch out your endpoints. Okay, now we're going to go back again to the general power rule for definite integration, and now we're going to be trying things with, no, that's not correct. Hang on, let me get the next page. Okay, that's the page I wanted. So we're doing general exponential rules for indefinite integration. So we're going to try the u again. So this time, here's our general format, and you can see that many of the times we make the u our exponent of our e term. Okay, so let's try that. So in this first problem, number 6, I can say that u equals x to the 1/2. Therefore, du dx will be 1/2 x to the negative 1/2. Okay, so that's your du dx. So what's my dx? So du divided by 1/2 x to the negative 1/2 is going to equal dx. But that looks very cumbersome. So if you divide by 1/2, you really multiply by 2. So let's bring the 2 up. If your x is a negative exponent in the denominator, if you bring that up, it's going to be positive. So look what happened this time. My dx is 2 radical x du. Okay? So let's do our switches. Okay, there are no endpoints, so we don't need to worry about that. So if I'm going to take this, my e to the x is now e to the u. The radical x is still there. The dx, however, is 2, and I have x to the 1/2, but we know that's exactly the same as radical x, du. Okay, this and this cancel. Bring the 2 out. I have an eu du, which is nice. So now take your antiderivative. So with e, write what you see and take the derivative of u, and since u is just u, there is no derivative, you're done, with the exception of having to switch back your u into your x. So this leads us to 2 e to the, not u, but e to the x to the 1/2, so it was radical x. And then don't forget the plus c, because you need a constant of integration since it's an indefinite integral. Okay, that's 6. Let's go on to 7. So here again, we're going to look for our u, and your y is to look at the exponent of the e. So I'm going to say that my u equals 2x cubed plus 4x. Therefore, my du dx will equal 6x squared plus 4. My du divided by 6x squared plus 4 gives me my dx. Okay, rewrite your expression. So my e is now e to the u, and then I still have 12x squared plus 8. Okay, look at my dx. My dx ends up being du over 6x squared plus 4. So what do you think I should do there? What if I rewrite my numerator so that it's 2 times 6x squared plus 4? So let's do that now. So I'm going to just put a single line through it. Make this 6x squared plus 4. And how about pulling out the 2? Because I don't need it inside anyway. Now at this point, I can cancel those terms. And what do I have left to take the antiderivative up? I have 2. And then eu, du, so that's not bad. So that's just going to be 2 eu plus the constant of integration, but remember you have to switch back. So that really is 2e to the 2x cubed plus 4x plus your constant of integration. So That's number 7. We've got one more in this section, so let's do that in the next page. Okay, here we have another U substitution. So this looks a little bit easier. So I see that my U is going to be x to the 4th. Therefore, my du dx will be 4x cubed. So du divided by 4x cubed will equal my dx. Okay, do substitutions. So x cubed stays the way it is. E is now e to the u. Dx is du over 4x cubed. So you should know what's coming next. X cubes cancel. The 4 can go outside as 1/4, so therefore that cancels in here. And then we will just rewrite it again. And so I have 1/4 times the integration of EU du. So that's just 1/4 EU plus C, and then do your switch. 1/4 E, and my U was x to the 4th plus C, and we're done. Okay, so as what usually happens, you can also do some other work for taking antiderivatives, and that other work involves a different procedure called integration by parts. So let's start that on the next page. So our textbook doesn't have a very good explanation of this, so I put a little bit more verbiage in here for you. So when you're doing integration by parts, it's a technique that's useful for integrands involving products of algebraic functions. So it's not just an algebraic function times its derivative, it's two separate functions, so you can't use the U substitution. So we had to remember how you took the derivative of a product. And you said left d right plus right d left, or u dv dx plus v du dx, which we can simplify as u v prime plus v u prime. So see where all that's going. Okay? So we know that in order to get an integration of a product, we're going to have to play around a little bit, and there is going to be a substitution, and it's going to involve u, but it's not exactly a u substitution, it's an integration by parts. So look, because we know that this is our product rule, if you take the integration of, that's u dv, so that's this right here, you can get that by saying uv minus the integration of v du. That will leave us with the integration of u dv. So here are some guidelines. Try letting dv be the most complicated portion of the integrand that fits a basic integration rule. Then u will be the remaining factors of the integrand. Okay, another rule. Try letting u be the portion of the integrand whose derivative is a function simpler than u. Then dv will be the remaining factors of the integrand. Note that dv always includes dx of the original integrand. Alright, so the best way to understand this is by doing a couple of examples. So I only have 2, because we're not going to go crazy with this, but I do want you to see a little bit of it. So let's do these on the next page. Okay, so in this problem, I say I have a product. I have x times ex dx. So what I'm going to do is I'm going to say, I'm going to make my u into my x. Okay? Then I'm not looking for, I am going to look for du in a second. So I'll say, okay, well, what is du then? Du is going to be, du dx is going to be just 1, right? So that's the derivative. Now, what is our dv? So our dv will be the e to the x dx. Okay, so just a little explanation. This x is our u. This e to the x dx is our dv. So we're taking the integral of u dv. So we're going to have to say that will be u times v minus v du. Okay, that's what's coming. Okay, so if I take this integral, what I'm going to do is I'm going to kind of rewrite things a little bit in my head. Okay, so I have my u, I have my du. Oh, I haven't gotten my v. So my v is just going to be, what's the antiderivative of ex dx? That is just ex. So if I know that I have now written u dv, I can solve this integral by saying u times v, so that's x times ex minus, and I have messed up the integral symbol there, the integral of v, what's v, ex, what's du. So that's just a 1, right? So what do I know now? I know that I can take this integral, and it's going to be 1 du dx, okay? Because I want, yeah, that's what I want. Okay, so what's my answer going to be? Well, I have to still take the integral here. That's just going to be ex. So what am I getting? I'm getting x ex minus e to the x. So can't I write this perhaps a different way? Can I say my answer is e to the x times x minus 1? Okay, and that's your antiderivative using integration by parts. Okay, let's do one more on the next page. Okay, so here's our last example, example 10, and I'm going to make my u equal to 7 minus x. I'm going to say my du dx, therefore, is minus 1. My v is going to be equal to e to the x dx, excuse me, that's my dv. My dv is equal to e to the x dx, so therefore my v is going to be e to the x. Okay, so let's solve this. So we know that if I have this written as u, the integration of u dv, to get my answer, I need uv minus the integration of v du. Okay? Okay, so what's uv going to be? That's going to be 7 minus x. My v is just e to the x minus the integral of v. What's v? That would be e to the x, and du dx is a negative 1. Okay, that negative 1 is going to flip that sign. So when I flip that sign, I'm going to get 7 minus x e to the x plus the integral of e to the x, which I know is just e to the x. So I'm going to get 7 minus x e to the x plus e to the x. So what should I do with that? If I wanted to, I guess I could do the following. I can write that as e to the x times 7 minus x plus 1. That will give me e to the x times 8 minus x, and we're done. Okay, there's another thing they talk about in this section, and that's called integration by partial fractions, and we're not going to do that piece. So what I'd like you to do at this point, try to do, so let me just change pages, try to do in your textbook the Chapter 5 review to see if you understand all of the integration. So I'm saying do 1 to 49 odd but I want you to skip 17, C and D, skip 19, and skip 37, and see how you do with that. So that means that you can check your answers in the back as you go. And that ends the 5.3 video. Thank you.